Hey, Alfonso, how are you doing?
Good, good.
How was the Devoxx?
Oh, it was amazing. So the conference, it was my first conference, and it
Hmm.
was like great. I mean, I met so many like nice engineers and people. I was like pristine. The organization was amazing. So the
This
people
is
said
true.
like, I'm
Hmm.
spoiled now because the future conferences, wouldn't be as good as this one. But it was very, very nice.
Yeah, this is true. Um, and we had, I think, since Devoxx 4 weekends. So, what the progress in Llama 3 Java, because your owner is working on weekends with Llama.
Well, I've done like a few minor stuff, but yeah, like I'm trying to actually create a more usable form of it because now it's just a
Hmm.
single file. It's just like a
Hmm.
toy project, right? Just a
Hmm.
nice demo.
Hmm.
So I'm trying to get it to work as a library, but that will take some time.
Hmm. I also wanted actually to fork it, just split it to multiple classes for instance, yeah, to create a model loader or something more sophisticated. But yeah, had no time for it. But I presented it as the WJX conference, and the reaction was that attendees came to me and asked me like 3 times in a row. So there is no binaries, no SO, no Python. So no, it's just pure Java, and no one could believe actually. So this was a good reaction. Hmm. And
Nice.
you did with Alina talk, and there were some GraalVM specific improvements, right? To Llama and performance improvement. So what was this about?
Right. So in the compiler, so the Graal compiler,
Hmm.
uh, 2 weeks before Devoxx
Hmm.
didn't support enough of the vector API
Hmm.
to run the model actually. But it happens that then you go to the fallback, just to plain Java code with the locations and everything. So the compiler doesn't produce efficient code if you use the
Hmm.
vector API. But one of my colleagues, Gergo, implemented the missing bits for the vector API. So
Hmm.
Graal support for the vector API is getting better and better. So now it's enough to run the inference pretty fast.
Hmm.
Actually, in the latest update, it got like another 10% performance improvement at ensuring that your vector code is actually vectorized, so it's compiled to proper vector instructions. So that's a good thing. So, but it doesn't support the whole API, so just a small subset.
Hmm. And so now it is 20% faster than C.
In C, let's say like C is also moving target. So Llama CPP is also improving every
Hmm.
week basically. So they come with these improvements in all different kind of platform. For example, the Java version runs pretty fast, even with Llama CPP in some cases, some configurations. In some machines, some quantization specifically. But for example, on Macs, it's not very fast because the vector implementation for Apple Silicon does not use any special Apple instructions. Just use the default Neon, which is a very old vector instructions. That is the standard on ARM, right? So one thing that would be very nice is that the compilers could support native, so Apple
Hmm.
specific instructions for the vectorization. So yeah, so performance. So I would say like we're still like maybe 10% behind C in most cases. So in some
Hmm.
cases it's better, in other cases it's worse. But
And what was the reaction? So are people excited and do you work, your colleagues, managers, or whatever about the stuff, or it didn't recognize? They already recognize what they have, or is now, after Devoxx?
well, it is a very nice demo, right? So and the the reaction was, I mean, so everyone was like, wow, the fact that you can do that in Java and it's
Hmm.
fast, right? Was very surprising. And we also showed that you could, with native image, compile the inference, so the whole program to a native executable, and it ran at the same speed as the JIT. So
Hmm.
it requires some tweaks here and there. But the fact that the Graal compiler is not as a JIT only, but also can do like an ahead of time compilation without profiling anything, just do a ahead of time compilation, and it runs as fast. So on that side, because I work on GraalVM, so it was actually very nice because you can use the vector API with some limitations as constraint, but you can also use it on native image, and you get the same speed as the JIT. For now, it just leaves as a nice demo. So because it's just like what Java can do, like we use the memory segment API, we use the vector API, all these sort of new modern Java features that we use in the Llama 3 project. Let's see how that continues to develop.
Okay, so regarding the one-to-one, how to call it, no profiling, right? So it just how to call it, statically compiles without any tricks, the GraalVM. But would it be possible to provide some additional information to GraalVM? Say, look, now you are in the vector mode, and add additional information that it should optimize very specifically just for the vector mode. Is it reasonable, or is it not reasonable, such a thing?
Well, yes. I mean, the compiler can do a lot of tricks.
Yeah.
But the problem is that the compiler needs to know. For example, one of the things we had to force to inline, right, was to the vector size. So how large are your vectors? So this is something that for ahead of time compilation, either you need to provide an implementation for all the possible vector sizes. So you need to emit a version of the method that works for all the vector sizes, and then at runtime pick the one you want, or you can just hard code, like statically initialize the class for the preferred species in your VM and use that. So the compiler needs to know. So if that's what I'm saying, like if you use the vector API in ahead of time mode, you need to ensure that the compiler sees certain things as constant, and then it will do the magic all on its own.
But we could provide this as parameter flags, right? So just would be less nice, but would be a good solution to start the compiler with specific information, just using these vector sizes, right?
Yeah, sure. I mean, you can force it yourself, so you can provide your own, right? That's what we did in the Llama thing. So you can. The other thing is that we can provide a feature where native image can ensure that your vector code is properly compiled. I think that's also very useful because one of the things that happens in the wild is that you write your vector code, but for some weird reason, it turns out to be slower than the Scala code. And it's like because you did something you didn't anticipate, that you stored your vector in a field, or you just called a function and you passed the vector and this function was not in line. So all this kind of mishaps can happen. And you have no clue as a developer what's going on. Why is my vector code slower when it shouldn't be, right? And in native image, we could do this pass to say, okay, like either your code is guaranteed to be fast as it can, or the build fails, for example. That would be a very nice feature, for example.
Would be GraalVM also capable to provide one file with the program and the model inside? This should also work, right?
Yes, so we could do that. But we refrain from doing that because I think having the model as a separate file for distribution, you have a program that can run several models, and then the model is just one extra file, right? Yes, we could embed the whole model within the image and memory map yourself into a memory segment. So in theory, yes, it's possible, but then your executable would be like 1 gigabyte or something like that.
Yeah, but if you're in the cloud, for instance, if you're in the cloud, right, this is what you need, because if you have in the pipeline and would you like to start something in Docker image, you will download one file from S3 or blob storage or whatever, and then just run it. So it is better to have one file than 2 or 3, usually, afterwards, right? And another crazy idea, would it be possible to parse the model with the weights and generate Java code with the numbers? You know what I mean? So you could actually read at compilation time, the model with the weights, because they are loaded to the vector. But we could actually create a Java code from that. It could be an array, I don't know, an hash map or whatever with all the weights, you know what I mean? So then we don't need to load the model. We can execute the Java code. I'm not sure whether it will be faster, but you know what I mean?
Yes. So what you're saying is that store in the image heap, in the native image heap, the weights as a byte array, for example.
Whatever. Yeah.
Yes, I mean that could work. The problem is that byte arrays are limited to 2 gigabytes, and sometimes for the bigger models, the tensors have more than 2 gigabytes. So that could pose a problem. But yeah, sure. I mean, all these kind of tricks you could do. Again, your image size will just be like floated, right?
Yeah. Not just crazy idea. So I saw your demo, and by the way, your talk was really great. So really, I appreciate your coolness. You were really calm and to the point, and you show. And the very best, for to the listeners is what I really like. You show their formula, and you said everyone in the room will understand that. This was like a big math formula on the right side, Java. This was my favorite of the talk.
Yeah, I had to make it somehow more entertaining because I realized that. So we started with the bullet points in the slides.
Yeah.
And then you have to you have to make it a bit more like visual, and then we added all these visual cues, so to say to people. Again, so please don't be scared. Don't be scared, right? This is like it looks very scary, but actually, it's just plain loops, and there's nothing there that. Yeah, because usually, you have this opaqueness behind all this, right? So like these old models are so complicated and so on, but there's nothing like magic behind that. That I can guarantee that. Yes.
Okay, now we covered Llama 3 Java and your project and your talk, Devoxx talk. And now back to your actual work, which is Espresso. So what is Espresso?
Right. Espresso is a truffle language. So some people call it like Java on truffle, but it's actually not specific to Java. It's a JVM on truffle. So it's a Java bytecode interpreter implemented on top of truffle. So it's a full-blown VM. So it has an interpreter and all the VM utilities. So it can parse and load classes. It can has a compiler like in theory. So it uses truffle. So via partial evaluation, we get the JIT for free. Anyway, so so I think the hardest part is all the VM functionality that we had to implement. I'm saying this because there was a first version of Espresso before I joined Oracle that used the hotspot class loading mechanism to load classes. So I mean, load the classes using hotspot and then somehow figured out where the bytecodes were and then had an interpreter on top of that. The problem with that is that then you were polluting the host VM. So because to load the class, you need to load the class in the host VM, right? And the reason why they did it that way is because it was too painful to implement all the class loading logic, all the class parsing in Java. So they just decided to reuse what hotspot was doing. But then that proved, for example, you couldn't load different classes. So, for example, you couldn't load a different object class. You had to, or a different string class, or a different so you have to share the classes with the host VM. And if you share the classes, then you also share the static the static initialization, the static variables, all that.
What you're saying is first, you are maybe too fast because GraalVM is already an open JDK-like VM. So you can just use GraalVM and launch your Java code.
Yes.
And Truffle is like, I would call it like meta framework, which allows communication between languages which are running on GraalVM, right? So I could call from Java, for instance, Python, or from Python, Node.js or whatever, and compile the entire thing in native image. So because GraalVM is also polyglot. This is the Truffle stuff. And what you did is, which is crazy, or what you did, what happened on GraalVM team is, there is an Espresso, which is Java implementation, which runs on Truffle or with Truffle, on GraalVM with Truffle. So it means the Java is also treated as Python or Node.js in the same way, so that the GraalVM is able to start Java as a foreign language and communicate with Python and Node.js. And now what we are saying is that you implemented the hotspot loaded classes in the host VM. So it means because Java runs on Java, you could only have one object, right? So one object, Java-lang object version, because it was already loaded by the GraalVM.
Correct.
So it was no more available by the application. So it was not a clean solution because the GraalVM interfered with application code.
Correct. So that was the very first prototype of Espresso. so yeah, that was an interpreter, like very rough interpreter, and it kind of worked. But then one of the things in the truffle is that you had at the time there was a JavaScript implementation, there was Ruby, there was Python, there was even the LLVM bitcode. So they had all these languages implemented on top of truffle, but no Java. So basically, you could run Java, but only as the host language, not as the guest language. And Thomas Rettinger, as the Graal boss, so he told me, like we have this Espresso project, and we'd like to have it, like implemented as a truffle language, like the full thing. I remember at the time I wanted to do truffle Scala instead, because I was very much into Scala.
Are you still into Scala?
So this days not that much, because I really don't have much time, but and the language has evolved in some like nice and not so nice ways. So so every time I try to do something with Scala, it's not as I can say as pristine as it was when I was a student, where it was like this magic shiny language where everything was beautiful. Anyway, so these days it's more like the tooling is a bit weird, and sometimes it's not very well integrated. Anyway, but so the language is still like a beautiful thing. But anyway, so going back to Espresso, so I want to do truffle Scala. Because why not? Just adding languages like crazy. But every time I say, we have this Espresso, why don't you just do like Espresso, right? And then you can also run Scala, because Scala is a JVM language. Mm-hmm. And as a student, I'd say, yeah, sure. But the thing at the time is that if I had knew really what I was getting into, I'd probably have said no, right? But as a student, right, I was clueless, right? Yeah, sure, let's just implement the JVM in Java, no problem. I will do it. And actually, this was my master thesis. So basically, my graduation also depended on that project to succeed, right? So it's kind of, I was betting everything to something that was a kind of like a moonshot in some sense, because how crazy is just to implement like a JVM like in Java? Just kind of like, but sure, I was like naive at the time and hungry, right? I really want to do cool stuff. So I started the project. So I started with a rough interpreter, and I started I remember the first. So when I kind of make it all kind of the very first rough prototype, I could run Hello World, like literally like system out println Hello World. And so if some the VM engineers, you will know that to printline Hello World, you have to load like 400 classes. So beforehand, you have to do a whole machine VM initialization. So if your VM can run Hello World, you're kind of done, right? So you're
system out, print line, print stream, object, system, and system with all the dependent object, maybe even, even logger then, because you have a system, then you have a Java util logger, the entire logging. So actually, these are quite an achievement.
If you print Hello World, your VM is already quite capable. So because you can already do all the, it goes, for example, all the initialization goes through scan the modules or the class path. So there's a lot of work during the start of the VM. Anyway, so I remember when I saw this Hello World, right? I think like this is the most, the hardest Hello World ever, right? Because the amount of things you require to reach there is crazy. So you need to implement GNI, you need to like all the class loading, the interpreter. Anyway, it's a really there's a lot of work to actually print Hello World. But once you have Hello World, means that you already like pretty much ahead, right? So you can then start to do other stuff. For example, you can start like implementing threads, because you can run Hello World with only one thread.
Exactly.
You can do threads, and so on and so on. So and then we started doing. There's a GCK. The GCK is the Java Compliance Kit. It's a huge test suite used to certify that certain implementation can be called Java. It's like Java certified or something like that. So literally, it's like dozens of thousands of tests that test every single aspect of the VM you can imagine. So from like all the collections, the debugging, all the different corner cases, like malformed classes, all sort of corner weird behaviors you can get on the VM. There's a test for that in the GK. So it was like a few months, maybe a year, and we got the GTK passing, so like it's all green, which means that Espresso was pretty conformant. And the funny thing is that there are places where hotspot, so there's the spec.
Wait a second. What it means? It doesn't mean that you had your own Java C. No, you didn't have Espresso Java C, right? So you used the you had the Java C in the Espresso.
No. So Espresso is just Java bytecode. So Espresso interprets Java bytecode. So Java C,
exactly.
You can run Java C on Espresso. But yeah, we use exactly. We use let's put it this way. We use just the regular Java C or the Eclipse compiler.
Exactly.
And also that was one of the very first tests as well, where we could run Java C on Espresso to compile Espresso. I remember.
Yeah, because Java C is a Java program, right?
Exactly. So,
exactly.
So at the time, Espresso was able to build itself with Java C because it was all Espresso. There's a little tiny native component, but everything else is just plain Java. So Espresso was able to compile itself, and then the time passed by a little bit more, and by the end of the Interchip, this was like even before the GCK and all that, Espresso was able to run itself. And I mean, from the practical point of view, this is not very interesting because it just, every level of nestedness just adds a slowdown. But from the beauty of the thing, all this, the compiler that compiles itself, the VM that can run itself, it's a very beautiful thing to reach. So by the end of my Interchip, one of the things I could show, right, was that Espresso was able to run itself. So Espresso was powerful enough complete enough to be able to load itself and run like some basic programs, like a Tetris or some trivial programs.
Cool. Right. So it's quite an achievement. I mean, so what do you have right now? We have Java as a first citizen language on Graal.
Correct. So as a guest language. So on Truffle. Yeah. And there's a few usages for that. For example, there's this dynamism on its own for performance. I wouldn't recommend it. So while the performance is not that bad or anything like that, there's always an overhead. So and it's very hard for us to compete versus C2 or the default OpenJDK or even Graal because they have a very tailored, optimized compiler for the host Java. So when you go through Truffle, you still have a compiler and you still have an inliner, but this is kind of like a generic version of it. So, for example, if you have code that is kind of simple, like usually like arrays and plain loops, then Espresso is as fast as Graal. So when you don't have much inlining, then it's just as fast. Literally. So and Graal is already pretty fast. So it's like an order of magnitude of 2 faster than Python. So this is it's not like it's a little bit faster. No. It's like as fast as Graal is. Then if you have a more code that have more abstractions, like we use interface calls, while Espresso does have inlining and a few optimizations, let's say it's not as performant as Graal will be. So you pay the price. Maybe it's like 2x slower or something like that. So yeah, on the performance side, that's one. So yes, so we have Espresso as a guest language. So, and one of the things that there's this interp in Truffle. One of the special citizens of interp was the host Java. So every language there's interp with the host. So basically, the idea is that you create a JVM and you embed Python or you embed Ruby or you embed JavaScript, right? But then you need a nice way to communicate with those languages. And there's something called host interrupt, where you can pass Java objects, and then you can get the objects from the languages back to Java and call methods and read members and stuff like that.
But what you usually get out is the Truffle API, right? So you are communicated via an abstract. So you are calling from Java, let's say, what I did is JavaScript. Yeah, I communicated with JavaScript. So it's not like you're calling a JavaScript method. You're always interacting. It looks like a little bit like reflection, right? So you have I remember a context. The context is not multi-thread, I remember, and you get out, and pointer to a function, whatever, and you can just call it. This is
Correct.
how it works. And
Correct.
the API is Truffle, I think, right? I believe.
Yes, so it's called the Polyglot API. So basically,
Exactly.
so this is how you communicate from the host Java to the languages.
Exactly.
But then with Espresso, what you have is that then you can communicate from the host Java to the guest Java, right? And one of the advantages of that is that then you have like its own VM. It's a very tiny VM, Espresso, where you have like a completely isolated. So usually what you use in hotspot is just create class loader isolation, but there's always problems with this. So because the code can do certain things and it can pollute your host VM. Anyway, so in Espresso, what you really get is like if you load the object class, it's not the same as the host. It's literally a completely new, different, separate object class. And
like JavaScript, but it happens to look like Java, right?
Exactly,
so this is,
exactly. So, and then since we are communicating with Java, then we have a little bit more nice interop. Let's say we're working on that. So basically, between host Java and guest Java, if you pass a string, maybe let's say like the passing objects, or you pass a byte array, passing all these kind of objects, it just works in some ways, and in the sense that the intro between the host and guest is a little bit better, I would say, than versus like host Java and I don't know, like JavaScript or some other languages that is completely foreign to Java.
Yeah, I remember I wanted to call Rust once from it is possible indirectly via LLM with GraalVM, and there was not even a string or whatever. So this was really hard, right? So I remember I had to do really strange things to call Hello World actually. So I can
right.
Yeah.
The thing with Wasm has the same issue, so it's getting better. But in the current version of Wasm, there's no string. So string is just a pointer and a length maybe, right? It's just like C. So literally, so to pass a string, you need to allocate the buffer and write the bytes and so on. So it's kind of like the native version of it. So, but between Espresso and Java and Espresso and the other languages, let's say like the interop is just much nicer.
Pretty cool. So what you created is a small cloud. So you can consider the GraalVM as a cloud. And you can have as many Java runtimes which are completely isolated and then they interfere with each other. So you could create a small serverless cloud where you're loading from externally Java code as a function and execute it, right? That's the first step.
But there are a few limitations to that because one of the problems that we still have kind of is the native code, because the JVM it has some native libraries. So if you want to read the file, it needs to call the native method. So, and the VM itself does it via GNI. There's a library called libjava.so, or there's the libnio, libnet. So there's a bunch of libraries, native libraries that comes with the VM. And for Espresso, what we do, just do the same thing as Hotspot, just reuse the library. So the Java code in the JDK will say, load libnet or libnio, right? And then link the Java native methods in the guest to this C method, right? And then just call it, right? So we did all the bridge. But the problem with these libraries on OpenJDK is that there are certain that there's a single VM in the process, right? So if you load the Java, there's no context for it. So it's literally you load it and it keeps some static state. And it does it only once per process. So, and then this limits, for example, the fact that you can run Espresso on Hotspot, because when you load Hotspot, it loads libjava, it loads like libnet and libnio and all that stuff. And then when you load Espresso, and you try to load these libraries again, then what happens is that the library is already there. So, and when you try to call the Hotspot, the native method, then it fails because the library already cached or created some state that is global.
There's like singleton, right?
VM.
So the libraries
Correct, exactly. So one of the things we use to work around this is to use in Linux there's this thing called DLM with opens like you can create a namespace for libraries. So you can load libraries in a separate namespace and you just load it again. But the problem with that is that this namespace are limited to 16, and they're not reusable. So basically, which means that you're limited to 16 Espresso context during the whole process lifetime. So this is kind of a bit limited. So we decided. So we still run in this mode because it's the way we run it usually in Hotspot. So we can run Hotspot and load Espresso, and then Espresso will load again all these libraries in these namespaces, so they don't clash with the Hotspot ones. The other alternative we have is that we have this project called Sulong, which is an LLVM bitcode interpreter. And the trick is that we decided, why if you compile the Hotspot or the OpenJDK native libraries to LLVM bitcode, right? And then use Sulong to load the libraries. Because the nice thing there is that then Sulong will ensure that, if the libraries are not native, then you don't depend on the native linking, so on the platform linking to do the heavy lifting. You can just delegate that to Sulong, and then Sulong can actually load several contexts, and then we'll load the bitcode again. So Sulong will take care of the isolation for us. And that's the other mode where that Espresso can use. Basically, we keep a version of the JDK where all the native libraries are compiled to LLVM bitcode, and then use Espresso to load the libraries via Sulong. In this mode, then we don't have the conflicts, because every Espresso context also has a Sulong instance, and then Sulong will create an isolated version of these libraries. The downside is then it takes a little bit more to warm up. Mm-hmm. It's not crazy, but still it's a little bit more slow to start up, because instead of just de-open the library, you need to Sulong needs to go open the library, parse the bitcode, and run something anyway. So it's a little bit more. It starts a little bit slower, but it works, and it solves the problem of the isolation pretty nicely.
Mm-hmm. And what about the performance? So setup is slower, but is this faster, slower, the same? The performance?
So let's say in Java, one of the nice things in Java is that the native code is really pushed where it's really needed. So it's not like in Python that if you want something fast, then you just write in C and dot. Right? Which means that in Python, it's every piece of code that needs some performance is already rewritten in C and then just a wrapper on top of it. In Java, it was kind of the opposite, in the sense that to write native code, you have to go through GNI. It was cumbersome. You have to write the library also. But actually, this barrier made that a lot of code is actually implemented in Java, and Java only uses native code to access things that it cannot do itself. For example, to write to a file, but really at the very last. At the border of the thing. So it's when you really need to perform an operation that you really need to code native code. And that's actually a very nice thing for Java and for Espresso, because these methods are not really performance sensitive, in the sense that you're not just calling native methods back and forth. In the case of Sulong, you're not calling a lot of interpreting a lot of LLVM bitcodes, but you're only calling native methods at the very bottom, at the very end of the execution, so when you really need it. So let's say while the native code is used only sporadically in Java, in the JVM, let's say performance is not as bad. So,
no, but what I'm more interested is, let's say I had a C library and an algorithm and bitcode, the same bitcode
stuff. You mean the Sulong performance?
Yeah.
Yeah, so Sulong bitcode and uses the same thing. So it's LLVM bitcode implemented on top of TOEFL. So there's an interpreter, and that's why I'm saying that at the beginning the warm up is a little bit worse, because you first run an interpreter, which is you're literally running kind of an assembly if you think about it, right? So it takes more time. There's an overhead compared to the actual native code, but then once it gets compiled by the Graal compiler, let's say there's also an overhead. I mean, it is really, really hard to beat C code, literally. So you're trying to compete against one of the most optimized, because you could say LLVM bitcode, but what you're really competing against is the client compiler, all these LLVM passes that it's
But client is static, and GraalVM could be smarter, right? So this is
That's one of the tricks. So that's one of the tricks that Graal uses. So Graal can do all sorts of optimizations and truffles.
Exactly.
So every language implementation can do a lot of tricks tied to the specific semantics of the language to make it faster.
Mm-hmm.
For example, where Clang or other static compilers cannot, Graal can perfectly use these patterns. So, like for example, it can speculate that the value is a constant. It can do inlining. So because ahead of time, you really need to inline in a more conservative way, or there's a lot of heuristics. But at runtime, you can profile and you can actually do the inlining depending on the profile, on what's actually being used on the program. Mm-hmm. So let's say, like from this point of view, yes, Graal can do a better job, but again, it's very, very hard to compete against like raw pure C code, like a heavily optimized code. But I'd say like performance is not as bad. So that's one thing. So it's the Sulan performance is not as bad. It's just like the warm up, because you have to interpret first and then you compile. That's the part that actually hurts the startup.
But you need the libraries just for starting a thread, the native thread, also the platform thread, and to write to I/O, right? So this is like where you need the libraries in Espresso, right? The native one.
Yeah, so to write to files, to write to the network, to open a socket. There are a lot of native methods that are really they don't need to be native. For example, like array copy is a native method. And actually, the magic that happens is that is an intrinsic in the compiler. So there's no array copy method per se, right? So it's just, I mean, in the OpenJDK, yes, but in the compiler, when you compile it, you don't call array copy. You just paste a snippet of assembly that will dispatch and do all the magic. For example, that's how it works in the compiler. But for example, like get class from object is a native method, but it's not really native. You don't go to C to get the class.
Okay.
The compiler will just give it a class for you, and so on. So let's say like
that's a cool trick. So then I understood. So it means some native methods in Java which are declared as native. This is not like there is no GNI call. The compiler looks at the native, say, "Oh, I know what you need," and the compiler returns the name of the class because the compiler exactly knows. Yeah, this is pretty cool. Yeah,
there's no. For example, when you do get class, there's no call. The call never happened. So the compiler will just literally paste the object reference, and that's it. So like, or read it from the object, right? So read it from the object header. So all these tricks the compiler can do. So let's say like in Espresso again.
You could do crazy things with that, right? So let's say if you are in pipeline, CI/CD pipeline, and I would like to have environment variables, right? What I could do, would be crazy, but I could have system get env, and the compiler will read the environment variables and return the values for me without calling, the environment. This would be like backed in constants at the compilation time, right?
Yes, and we can do all these tricks. I can tell you. So, for example, we have another prototype where we implement most of the native methods used for I/O on the network in Java. Because if you want to write to a file, right? The last call you do is some write something, and then you pass some byte array or some byte buffer or whatever. But in Espresso, you can implement that just in host Java, right? So instead of calling to C, you can just call to host Java to do the same thing, and then you don't have to really call you don't need to really load libjava. So it's what we'd call like a nativeless version of Espresso, where you don't load any native libraries. The only problem with that is that then we are restricted to a subset, like a core functionality of Java, because if you don't allow native libraries, you're restricted. So you can do I/O, but like in a restricted form. You can do restricted means that it works. And then, for example, one of the things we did is that then you can completely virtualize the VM, because the VM. So it's like a virtualized VM on its own. So Docker offers these utilities to sandbox the context, so you can create a guest language. And you can say, I don't want this language to write to a file. And you provide like a file system it has access to. So with this virtualization layer, where we hook other native methods in Java, we could achieve the same effect, right? And the nice thing here is that the worst thing that can happen in this mode is that your context will throw an exception. So there's no way to crash Espresso in this mode.
Virtual Java, you know what remembers me of? I had a chat on this podcast with Gil Teen about he created Azul machine, so real hardware, and they had Azul JVM. So this was, and they run the code, but the code was not executed actually on the Sun machine. Rather than entire execution context was passed to the Azul system machine. So and they virtualized the environment with hardware. For me, the Espresso is like virtualization in software, but this is very similar principle what they did back then, which was crazy actually with the Azul system machines, Vega machines. Azul Vega was the name. And the second thing, what remembers me of is serverless Java functions, because if I run, for instance, Java as a Lambda, I have basically one method which gets called. I get the context from outside and then do something with. And I could do something like this with Espresso. So let's say I have a GraalVM, this is the host, this is my small cloud. And I'm loading from outside as a string. This should work. This worked with Node.js, my Espresso Java, right? And then I can replace it between calls. And then let's say Espresso would be pure Java. Then I could still, on my host machine, get access to the operating system and pass it as a context to my function. And the function will call and say, give me the byte array or whatever, and I will get it from GraalVM. So this would be also possible, completely isolated environment. So this is actually pretty cool, I would say.
Yeah. So I mean, in Espresso, so there's the sandbox, and then we have some users that use Espresso exactly for that, so to isolate. Another nice feature of Espresso is that it's very hackable. So, for example, we have this called like my current. He can one day say, like, I want to implement continuations on top of Espresso.
Oh.
You say, sure. So 1 month later, done, right? So he really implement not only continuations, but serialize. So you can serialize the continuations and so on. So for example, for you to get an idea what the continuation is, maybe people are familiar with what the Python generators are. So you can have this yield in Python where you can call a method and then iterate over. In Java with continuations, we can do the same. So in Espresso, there is a yield, right? And then you can literally iterate over a method that just continues yielding to you, right? And the way it's done, it's like, the method is replayed and so on.
So the continuation for me means I can freeze the state of the entire thing, and then at the next call is there. It's more like a state machine which is frozen in time, right? So
this is implemented in Espresso right now, and it will have been way more complicated to implement such a feature, for example, in Hotspot, because it's a secret like the C++, or so all the complications of a very complex system. And Espresso, you just do it in Java, right? So it was.
But I think in Java there's internal API which is based on virtual threads. So the virtual threads API does continuations, but this is hidden on you are not supposed to use it, right?
Exactly. So let's say like the trick is that on Hotspot they do have continuations, but they don't expose it to you. So they only give you the result rate. Exactly, it's the same thing. So, but in Espresso, we support continuations in the language. So we have this thing where we serialize the stack, and then you can, for example, one of the nice places or the features of this is that you can go continuations, serialize the stack, right, and then kill the VM, right, and then restart the VM, and then pick up again the serialize the continuation, and then resume the execution there, for example.
So now you have the serverless cloud, even better.
Well, there's some limitations, right? So in your stack, you cannot have like weird objects in your stack, so right? But if you have like a relatively generic computation or something that is not very complicated, right? Or that you want to checkpoint the state, right? Then you can do all these sort of tricks. So because it's not only continuations, it's serializable continuations. So that feature is implemented in Espresso. And
so you can have our small GraalVM cloud could, someone calls your function all the time. It calls and calls and calls. It's warm. point of time, it stopped calling that. So we wait 1 minute, then we serialize the context to a local file. And then someone comes, so we can restore the context to a warm JVM again, and then we can proceed calling. So this is incredible.
Yeah.
And we could have a multiple versions, I assume, of Espresso at the same time inside one GraalVM. What? Right?
Yes, correct.
Yeah, this is, you have a cloud.
Well, so also one of the other problems with Espresso is that there's a little bit of footprint overhead, right? Because every time you load the context, you have to reload all the classes and all the metadata again and again. So we have this feature to share.
Wait a second. But it is smaller. Than GraalVM, right? Entire GraalVM. So Espresso inside GraalVM is smaller than 2 GraalVMs, right?
I would say so because GraalVM loads many things. I'm not talking
exactly.
native image. Native image is a different bit.
Because the idea would be the GraalVM you install once and you have multiple Espressos for different users at the same time, so it would still save memory and resources.
Well, so if you share the context, the metadata, yes. So in Truffle you have this concept of an engine, right? It's that the core thing is where you can share. So and then you can create from the same engine different contexts, right? And they can share information. For example, if you load classes, we can share all the metadata, right? All the structure of the classes. You don't have to reload it again, for example. And in this scenario, if you load several Espresso contexts, then you can share all this metadata, and you don't have to reload it again, reparse it, recreate all the objects and all that.
It's something like this app CDS or how it's called. So it's like the class data share. What is
it's a similar thing, let's say. But the problem with the CDS and in Espresso is that you cannot share the objects per se, right? Because of the differences in the initialization. So we want every context to be independent.
Yeah.
And so in that sense, every context needs to have its own class initialization state. For example, like some classes may be initialized in one context, but not in another. Yeah. Or the static fields can have different values in different contexts.
Yeah, but similar concept for me,
exactly. So in FCDS, I think you also have this sort of sharing, but also you can actually, for example, have an initialized class or something like that. In Espresso, we don't share this. We only share the how to say, like immutable or the class metadata, let's say. So people also wanted to share, for example, code. So if I create 2 Espresso contexts, can I share the code, or like code means like compile code, but that's a little bit more tricky for the same reason. So if you have a function compiled for one context, maybe that function will include some knowledge from that context to actually be faster, right? But if you share it, then you have to drop context-specific knowledge from the compilation. So it's a bit tricky. So we have a few experiments trying to achieve that, but that will be also very nice, because then you could be able to load one context and then spawn like many different contexts, and then they will all start like warmed up, right?
So for the framework or for foundation or for libraries would be interesting. Let's say we have the GraalVM cloud context, which provides the access to I/O, whatever, and this is the same for all context tests, right? But what you're saying is maybe this library is used differently per context and is optimized differently, right? So this is the problem, because even if it's the bytecode is exactly the same version, everything, it is used differently by different business logic lambdas.
Correct.
That's the problem. Okay.
Yeah, or the initialization order changes, or you pass a different system property and then change some behavior. Yeah. All sort of things can happen. So for now, we don't share code. We only share the metadata.
Yeah. But what is the ultimate goal of Espresso?
Well, currently, as I mentioned, running Espresso on its own has no practical use. But Espresso is kind of helping Graal or Native Image and all the Graal project to add more features to it. For example, recently we're working on a debugger for Native Image. The way that debugger works is that it will. So let's just put some background. In Native Image, when you compile Native Image, the only way to kernel debug it is with GDB. So literally, you just open GDB and then you have the see experience, right? Let's say. And in order to do that, you need to build an image that is non-optimized. So you need to do O0 and then include all the debug information and so on. Of course, the experience of using GDB on the console, it's something that regular Java developers, me included, are like really not want to do, right? So we prefer to just connect your IDE to your VM and then use your existing tooling to debug your Java applications. So now we're working on this debugger for native image, where the native image, we embed all the information necessary for the native image to actually serve a debugger, and in the same way, or in a similar way, because it does some limitations, in a similar way as if it were like a regular JVM. For example, you can put breakpoints, and you can inspect your locals, and you can even run snippets of code in a native image, which is also very surprising, because you would say, yeah, but native image, you cannot execute new bytecode, you cannot load new classes. No, you cannot do that, but because of the way all the protocols are implemented in IntelliJ in particular, it's very interesting. So you can actually run like snippets of code. Well, the only limitation is that in these snippets, like the evaluate window in the debugger, is that you can only use classes and call methods and fields that are included in the image, right? In a regular hotspot VM, you can load new classes. In the native image version, you cannot, because it's a closed world. But everything that is included in the image, you can observe from the IntelliJ, from your regular tooling. There's still some let's say limitations or the things that are not very polished, and that's the reason why it's not let's say officially released. But we're working on it, and ideally, people can build a debugger version of your native image. And one of the nice things here is that you don't need to build a non-optimized version of the native image. You can do it like all three, right? Native, and it will still work. So, right, basically you connect to the debugger, and then the methods you're debugging will be slower, of course, but then everything else will be unaffected. So that's also a very nice feature of this debugger. So for that project, we're using Espresso, or a version of Espresso, let's say like Espresso interpreter, to do all this functionality. And then there are other projects that we're working on for native image and for Graal in general that use Espresso as a foundation to build them. For example, now we want to add some dynamism in native image. Let's say like you have a native image where you kind of precompile some ahead of time compile like a part of the image, but then you still want to load some classes at runtime, because you cannot avoid it or something like that. So then with Espresso, or with a modified version of Espresso, let's say it's not Espresso on its own, we can achieve this mode, or do this kind of provide this functionality. Anyway, so this is still like a very experimental. It's still like not even a prototype yet of these things, but these things that Espresso is being used for, right? Because now we have a kind of very compliant interpreter, and then with all the VMs, so we can parse classes, we can load classes, we can resolve console pools, all the hard things or the complicated things that a VM would do, we have implemented just in Java. So why not just reuse them in places where it can provide either a good functionality for users, or some better functionalities for the VM and so on, like the debugger, or the dynamism, loading dynamic classes and so on.
I have two other use cases, completely different from immediately. So one, what I did years ago, I hacked my heating, and just so I observed all the sensors and decided, if the sun shines, I don't, I don't activate the burner, for instance. And this was very trivial. But what I wanted to do is, to make the rules replaceable, and the rules were basically if else. It was very basic, but this already helped a lot. And what I used back then is Groovy, and everything was Java, but I used the standard Java API for scripting to load Groovy from outside, which was stored in a database, and I could replace, the rules between every call. And the only reason I used Groovy because I had to. but now it uses Espresso, for instance, right? So because the cool story now is I can actually write unit test everything as this is Java and store this Java in a specific location and load on demand on GraalVM. So it means all the hacks I had to do with JavaScript, NAS1 back then, I use NAS1 only for the purpose. Remember my NAS1? It's like JavaScript, right? Yeah.
Mm-hmm.
So and I use NAS1. What I always did is I had a Java interface and was implemented by JavaScript and was called by Java logic. And we had a replaceable business logic, basically. So we can reload the logic on demand. And because it was executed on Java, it was somehow safe. And now Espresso is the way to go. Even better, So now I have a GraalVM. I can load Espresso classes and run them. And back then, I migrated, because NAS1 was no more available. I migrated the my functionality from NAS1 to GraalVM and the Polyglot JavaScript environment, and it worked smoothly. So it was actually one-to-one migration, and it worked. So this is actually the first one. The next one is even crazier. So the next one, if you work with LLMs, so the proper ones, so they are not capable to have calculations, for instance, whatever, and they have functionality to generate code. And they are already products on the market, so we can say if you don't know how to calculate, generate. I'm not talking about functions or tools. I'm talking about something different. And then the LLM generates code for you, which can be run somewhere. And all the code interpreters I've written in Python, because people don't know that you can do it with Java. So with that, now the LLMs could generate Espresso code, which is then safely executed by GraalVM.
Yes.
And because it is Espresso code, we can actually pick it and write unit tests for it. So if the LLM hallucinates, we can actually say, okay, write the code and unit tests for it. We can look as Java engineers on Java developers on the unit tests and say, okay, looks reasonable or not, right? So this is two, again, interesting projects, I would say.
Yeah, so actually, I remember in LangChain4j, I did this tool support for GraalJS, right? At some point, to implement this, exactly that, so they could evolve some JavaScript code using LangChain4j. But of course, somebody else just submitted the PR, and then they have the same functionality. But sure, so using Espresso, you kind of achieve all this. The problem is that all this sandboxing and all this functionality, there's kind of a missing loop of feedback, right? So in Espresso, we are focusing on certain aspects or certain others, but it's very hard to implement or to commit to certain features if there's no demand or nobody kind of asks for it, in the sense that people don't know what can be done, right? And since you don't know what can be done, they don't ask for it. And since you don't ask for it, then we don't implement it, so it never gets done. So basically, the way we work on Espresso, we have some internal users. Basically, we implement all the features these users need, right? And that's what we do. So that's kind of the main goal for them. But there are so many things you could do with Espresso. But it's just a matter of with Espresso, it's a core VM. You can hack on it and you can do very cool stuff. But what you really need? So you really need like a strong sandboxing, really strong. I mean, something you cannot we call it we can have safe unsafe in Espresso. It's not safe that you cannot break out of it. Because you cannot write to some random location. No, that it would disallow all that thing. So all this, so for example, but again, all these features that are perfectly possible in Espresso. Right now, let's say let's say if you use unsafe, the way it's implemented right now, you can actually crash your VM, because you can just unsafe put to some random address and you can kill your VM. Of course, we could add all this unboxing and so on, but it's kind of a feature that needs to be asked for.
So what I'm surprised that the Oracle Cloud infrastructure managers are not pinging you, because this is actually, you have 80% of pure Java cloud actually available, and with Llama 3, even LLM inference with pure Java. And I know because Chad, you attended my talk, so this was like high-level enterprise, and this is actually what I get the questions a lot. Look, we have already enterprise applications written completely in Java. Now there's a request from marketing. We have to integrate LLMs. How to do that, right? So and we have the answer. And this would be actually for Oracle. So I mean the Oracle Cloud people and Java. And the Java people actually the perfect killer use case. Because no one else, everyone tries to be polyglot, and they could say, look, if you are Java, there's the Java serverless based on GraalVM with even LLM later support. And this is actually a huge use case, right? So this is what I'm surprised that it doesn't happen. But maybe other clouds will pick it. So who knows?
Let's see. So this sandboxing, I think it will be very useful. And actually, people will. So now that the security manager is being deprecated and removed, right?
Yeah.
I think Espresso would be a very, very nice replacement. Yeah. Because then you don't need the security manager. Kind of your VM, if it does something weird, it will just, like throw an exception and the context will die, the Espresso context will die, and that's it. But there's no need for the security manager, kind of, right? Because it's something that is completely sandbox, for example. So
but think about it. In regular cloud environments, right? So you have the EC2 machine or hardware, then you have a virtualization layer, then you have a kind of JVM indirectly, and then you have the actual program, right? Mm-hmm. But if you know already, okay, I'm just doing Java, what I will do is I will just pick, a small machine, just hardware, then install GraalVM on it, then provide some instrumentation, and then the Espressos are running as user services. And maybe per user, every user gets an own GraalVM to have even more isolation. But this removes all the abstractions between, and even so, Espresso is a bit slower than GraalVM and a little bit bigger. It is still a fraction of the entire overhead you usually get with the full virtualization stack, right?
Yeah, I will use it for example, for either user code, or for example, for these like the continuation features we have.
Yeah, I mean continuation are crazy. This is.
We also have like the class reloading at runtime. So we do have these features where you can reload classes, you can add methods. All these things also work on Espresso, which for some use cases is actually very nice because you don't have to restart the whole thing.
Yeah.
The application, you can just load it once and kind of like continue working there and tweaking there, and so on. So Espresso actually, as I mentioned, is a very tiny and simple JVM on its own. I really hope that it picks up at some point and find some nice use cases somewhere. So let's see.
So perfect. So I have to reinvite you back, to talk your debugging and Espresso deep dive polyglot, and it was nice to chat with you, and always interesting stuff you are doing. And where people can find you on the internet, LinkedIn.
Yeah, on Twitter, I don't check much Twitter these days. So basically, I think all my information is in my GitHub page. Is like GitHub/Mukel MUKEL. There you can find my Twitter handle, and you can find all my addresses to contact me, and that's it. My code is also there. Yeah, some of it.
Your spirit.
Yes.
Okay. Thank you. It was a nice conversation.
Yeah, thanks for the invitation, Adam.